Good afternoon, everyone, and welcome to session one of our course on Big Data and Hadoop. My name is Anjana, and I'm part of the team here at No Big Data. I will take a few minutes of your time to take you through what to expect of this session and to introduce you to No Big Data. This session is going to be about 3 hours long. The first half will focus on what big data is and why it is relevant in today's world, and the second half on Hadoop infrastructure, Hadoop architecture, sorry. There will be a 10-minute break, about an hour and a half into this session. That's at 3:30 p.m. You can use the chat window to interact with the instructor. You can help the instructor respond to all your queries by keeping your messages short and avoiding chat language. For anybody who is making notes, please sit back and relax. We have all your contact details. We will be sending you the presentation and a recording once the session is done. So before introducing you to Big Data and Hadoop, let me quickly take you through No Big Data. Our primary focus is online trainings relating to big data and data sciences. We're thrilled to provide you with instructors who are industry experts. You will soon see that during the session. As part of the course, we provide access to cloud labs. This is a unique feature to No Big Data. This is a cluster that you can use as used to play around with whatever you learn during the classes. This feature is unique to No Big Data, like I said, and it is something that we are very proud of. It will give you a feel of how things work at at organizations at big organizations that use big data itself. So course takers are also given lifetime access to our learning management system, which will include all the presentations, recordings, assignments, quiz work, and project work. You will be able to use our cloud labs to complete a real-life project, at the end of which you will receive the certificate of completion as well. So you'll also be part of our alumni group. We like to refer to it as Knows Big Data, which will keep you posted on the latest things when it comes to big data itself. So let us move on to today's session. Our instructor today is Sandeep Giri. I'll let him introduce himself and take it over from here. Have a great session, guys.
Hi, this is Sandeep Giri. Can you hear me clearly? Good afternoon, everyone. Is my voice coming through? Are you able to, or you are not near the keyboard? So let me just unmute one of you. So I'm unmuting Neela. Okay. So, hi Neela, will it be possible for you to type your questions in the chat window? Anjana, are you able to hear me?
You come here.
Yes, Sandeep, I'm able to hear you clear.
Okay.
Yeah, Sandeep here. Are you able to hear me?
Yes, yes, I can hear you.
Yes,
And
just
so
yeah,
I
just to let
understand.
you know,
Yeah, go ahead.
sorry, just to let you know that we are using kind of VoIP to connect to this audio. Okay,
Okay.
and of us have kind of connected through the systems, but we will keep the Wi phone on mute. And there will be one person, Ramya, who will be collating all the questions and asking whenever there will be a question session time.
So my question is that will all of us not be able to ask question immediately by typing?
No, because like we don't want like not everybody has a laptop, and
Okay.
we don't want Yeah, we are sitting, all of us are sitting in a conference room,
Okay.
and we just want to give it a kind of more of a classroom session, feeling, so that focus will be there.
Uh, okay.
Do Do you see any concern?
Yeah, because see, generally, my primary motto is to answer as many questions as I can, so that nobody is left behind. Okay. And typing question is far more easier than asking questions over voice, or routing those questions through anybody else. So I was just
So
wondering what?
how about we will keep the phone in the mute and we'll ask those questions through chat window.
Yes, 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 yes.
Is that okay?
Yes, yes. So I would actually
Okay.
appreciate if you, I mean, all of you as well log in as well. That will be great for the session. Okay. And I mean, the online session, when individual can type and ask questions, so people generally ask more questions as compared to a classroom. So that is the biggest benefit of an online session, because in an online session people ask more doubts, people are more open to asking question as opposed to the classroom. Okay, so that is why I was recommending that if you all of you can also log in, so that parallelly we can wait. There's no hurry. We can wait. In case today's session gets delayed a bit, we can extend one more session. That's not an issue. But important thing is that we all should be able to interact uh, really well. That is my main agenda. All right.
Yeah, but to log in, everybody they will have to go to their own desk, because we are in office, right? And
Okay.
that is the only problem. So they can do that, they can log in, but they will have to go back to system, and some of them have raised an issue of some issue is there in internet, like
Mhm.
security issues.
Have at least two to three laptops, so that people can ask questions quickly.
So you join, and so you join.
Basically, multiple people can have access to the question keyboard, so that they can quickly type the question. And
Okay.
okay. S- so, so
What?
so once you are done with it, just let me know so that I can start. There's no hurry. Just be comfortable in what in the whole communication, so that I mean, there's no hurry. So make yourself comfortable, and let me know. We can start. All right. I'm putting myself also in the mute till the time you guys start. Okay. Hi, let me know once you are ready so that we can start. All right. All right. Good afternoon, everyone. This is Sandeep Giri here. It will be great if you guys start with your introduction also. Okay. So that I would know that I would have a little bit of understanding about my audience, and accordingly I will go either deep or shallow on various concepts. All right. Great. Great. So again, so is my voice audible to you? Is it clear enough? Great. Thank you, Chetan. So the session is getting recorded, and session and slides and everything, including quizzes, questions, future references, everything will is available in the LMS, for which the email has been sent to you already. All right. Now, a little bit about myself. I am Sandeep Giri. I did my graduation in 2002. Then I worked for an interesting company called DE Shaw, where I was working on a cluster of 10,000 node in the year 2002, when the other people didn't even know what exactly is big data. The term was coined later on, though we had been working on big data since that time. And ironically enough, our data was so big that we could not download it through the internet. So our data used to come using ship from New York to Hyderabad. Okay, I mean it used to come to India via ship, and then it used to come with traditional means. That used to happen every week and every month. All right. So that was in DSHA, where we built big data systems before even the term was coined. Then I founded a company called T-Bits Global for, and we built a document management system for large enterprises, and lot of construction companies use that software as of today. Okay. After that, I joined InMobi, where I worked a lot on data sciences part, and I built a recommender, basically a recommendation engine, which shows the recommendation instead of showing the advertisements to the people who are using apps or who are using playing games. Okay, so that's what I did at InMobi, and this recommendation engine, which shows you the recommendation that if you are playing this game, you might also like these games. So this recommender engine was based on 200 terabytes of data. Okay, so we had 200 terabytes of Apache logs. of past around 8 to 9 months, and we churned that to do a lot of interesting stuff. That was at InMobi. Then at Amazon, I built something similar to Apache Storm, which is there in the open source, but a better version of it. And also Amazon's detail page, which is the mobile version of it. uh, I had it that design. Okay, so most of my career has been into dealing with humongous amount of data. Okay, most of my career has been into dealing with humongous amount of data, and therefore we started a no big data in 2014 April. All right, that's about me. It will be great if you could also write a small introduction about yourself. All right, so use the chat window and please introduce yourself. So the way these online sessions happen is that instructor is giving. I will be showing you. I will be explaining concepts, interacting with you, slide by slide, and you keep on asking your questions. You do not have to wait for me to finish to ask a question. You keep on basically you keep on asking question, and whenever I get a break, as in I finish explaining something, I pick up your question. So you don't have to wait till the point I finish. All right. And there is no need to take notes. Take the notes only for your own convenience, I mean, own clarity of thought. Otherwise, all these slides, everything, including this recording, is going to be available. So your primary focus should be in understanding what am I saying, and then asking questions based on that. All right, and be based on what is being taught. All right. Okay. So Chetan has been in ITC for 1 year and working mainly on J2E. Great, great. Ramya is around 10 years of experience and good, good. And Ka- Karthik is on web enabling technologies. Great. And Nasruddin is around 10 plus years of experience. Looking forward to know. Okay, okay. Vishnu is 7 years of experience in different domain and okay. Okay, currently I'm switching from B2B to big data. Great, great. All right. All right. So keep introducing yourself. I will again go through it. Till then, let me just describe a bit about today's class. So today we are going to deal with what is big data, understanding big data, and then the most important component of all of the Apache Hadoop ecosystem, which is HDFS, is what we are going to talk about today. All right. All right. Saket is 12 years of experience. Great. We have got a very great team here, and I'm going to have a very good experience interacting with you guys, and we'll learn from the discussions which happen. All right. Great. Great. So it's a wonderful set of people, and I've gone through everybody's profile, whatever has been written here. Great. Great. It's just great. All right. So I'm going to go first into the big data part. What exactly is big data, and why now? What are the various use cases? And then I'm going to discuss what exactly is Hadoop and what are the various components. And then we're going to talk about HDFS. All right. Now, so before I start explaining, let me understand from your side, what do you understand by big data? What exactly do you understand by big data? Okay, okay. So there is an audience of 3 to 4 years of experience also. Good, good. All right, all right. So we have basically most of you are into the technology. Most of you are uh, into the Java or J2E technologies, and there is a I mean people starting with 2 years of experience upwards. Good. All right. So I'll keep that in mind. So Chetan says that as the name suggests, huge data may be structured or unstructured. All right. Anybody else? About big data to deal large amount of data in chunks. Okay, that is Karthik. Good. All right. Open source, scalable, faster. Good. Good. That's Vishnu. Similar to CLOB as used in SQL. hmm So CLOB is very small part of data. Okay. In SQL, when we define a data type to store binary data, we generally define it as either blob or clob, right? So that's a very small section of it. Okay. All right. So that's it. Great. So moving ahead. So big data is essentially, I mean, this is something which we all need to understand. The data of really, really huge size. And to process that kind of data, you need different kind of tools than what we have as of today. I mean, what we have as of today is mostly relational database tool or the file systems to handle that kind of data, right? So, so when your usual file systems or usual databases cannot handle the data, you say that it's a big data. And mostly you would require a distributed computing architecture for processing that kind of data because a single computer cannot handle this kind of data. So whenever you need multiple computers as well as a software that can run on multiple computers to handle the big data, the data you have, then you say that you are dealing with big data. So out of this, the third point, which is distributed architecture, is of the most significance, right? The fourth point is the data could be structured or unstructured. It could be semi-structured. It could be what it could be in whatever form. So the most important part when it comes to big data is third one, which is distributed architecture required, right? It because when I say data of very big size, it does not make sense. Okay, how big are we talking? Are we talking about few gigabytes, few megabytes, or are we talking about terabytes or petabytes? Similarly, the second point which says that cannot process using usual tools does not make much of a sense, because usual tools, what do we mean by usual tools? After some time, if the Hadoop becomes the, I mean, if a certain tool is not usual, uh, some particular format, if it is not usual format, we don't say that it's a big data. The third point is the most significant one. So when you hit a roadblock, when you cannot use your usual file system or databases, and you require a distributed architecture to solve your problem, then you say that you are dealing with big data. All right. Now, this is the standard definition which is given by IBM. So if somebody is asking you some, if you have to take a call on whether something is a big data or not, this slide, the first slide, would help. While this one is a general one, if you give the first answer, people may not be impressed with you. People are quite used to this definition, where we say that big data has got four characteristics. Okay, earlier it was three, then it became four, and now this last year it has become five also. They have, IBM has added one more V into it, which is a V for value, right? So I mean, I don't know if they are they are going to keep adding V to it, the dictionary will exhaust. And so, okay, let me describe this definition, because this definition is something what people expect. So the definition says that big data has got a characteristic, and big data and big data analysis are two different things. Big data is just a characteristic adjective to the data. Big is an adjective to the data, and it represents very huge data. All right. Now, so keep asking the question. If you have any question, keep asking the question. And whenever I take a stop, I will take up the questions. All right. Feel free to ask the questions. And these sessions, our sessions are mostly about answering your questions, because most of this, whatever we teaching you, you would might be already knowing. It's just that you might be having a lot of questions about things. All right. Now, the first characteristic of big data, as per this definition, is volume. When by virtue of volume, when by virtue of volume you are not able to handle the big data, okay, by virtue of the volume you are not able to handle a data, and you require a distributed architecture, then you call it big data. Or in case your volume, the data volume is maybe low or maybe high, when there is just too many requests coming in from all the users, and all the, there are too many API calls, too many remote requests coming in, and which means there is a lot of data coming to you. When request coming is in the form of, in the form of, uh, I mean, packets, and packets are nothing but electrical signals, and electrical signals are nothing but electrons moving, right? So when there's a lot of movement of the data, and and there may or may not be the data may or may not be stored, and the capacity may not be high. In those cases we call that it is because of this velocity we had to put so many servers, and we had to change our architecture into an architecture which supports big data. And let me take an example. So can somebody give an example where velocity is high but volume is low? Volume means data at rest, while velocity is data in motion. Can anybody just give me a random?
First one, मतलब,
Should I
on the
mute?
class में.
Should I mute you, Satyanan? I think it's by mistake. Great. Live video is a good example. Likes in Facebook, yes. And okay. So velocity, yes. Yes. All right. Good, good, good. You can take the example of this class itself. As I'm talking, so there are 10 people right now, and the velocity is too high. Had I not been storing or recording this video, the volume could have been zero at the end of the session because I did not store, and probably GoToMeeting is also not storing anywhere on the server, right? So effective volume is quite low in these meetings, though the velocity is quite high. If you see that at the end of 3 hours of today's session, there will be around 1 GB data transferred from me to GoToMeeting servers. GoToMeeting is the software which we are using for today's communication, right? That will be like for how much time? For 3 hours. So I transferred 3 GB or 1 GB of video from my side to the server side. All right, to the GoToMeeting server. Now GoToMeeting has transferred that 1 GB to say 10 people now. So effective transfer of data is around 11 GB, right? And there is no storage. So in these cases, when there is a low storage and there is a lot of data that is getting transferred, then we call it the velocity is too high. Velocity of the data is too high, too many requests coming in, but there is nothing gets stored. So there are cases where there is no volume and there is high velocity, but sometimes there is a high volume as well as high velocity. In both the cases, I mean, in both the cases, the data may be a big data, provided you require a distributed architecture. So distributed architecture is the key term in the all of it. And again, distributed architecture is something where a software that can utilize multiple computers, multiple hardware, multiple machines to solve your problem is called a distributed architecture software, right? Twitter feeds is one good example. Thank you, Saket. Yep. Now, third characteristic of the data that might lead to variety, that might lead to the big data is variety. Okay. Third characteristic of data that might lead to that might lead to big data is variety. All right. Now, how would variety lead to the big data? How would variety lead to the big data? Say, for example, let's take 50 GB of Google Maps. Let's say let's pick up the maps of maps of Karnataka along with the traffic details. They will hardly be 50 GB. Okay, so there is no volume. I mean, if you see 50 GB is nothing when we talk about volume. You can store it in your hard disk. All right, it's very easy nowadays. You have 32 GB and 64 GB, even USB drive. So 50 GB is nothing actually. Now you have very low volume and there is no velocity. This data is not very much changing all the time, right? But our problem statement is such that given this kind of data, you have to find a path from one location to another location, and that is what makes it a variety, because finding the path is a cumbersome process. It's a difficult process. You need finding the best path based on traffic, based on various kinds of junctions, and all sorts of ways. You will have a tough time to find the best path from one point to another in a reasonable amount of time. And that's when we call that even though our volume was low, velocity was low, but due to variety, we had to use multiple computers, and therefore our data is big. The other case could be, say you are doing a video analysis of, say, 50 movies. Okay, you want to figure out a certain pattern in all the videos. Although 50 GBs is not a big data, but just by virtue of variety, just by virtue of the kind of problem we are trying to solve, we might have to use multiple computers, because one computer might not be able to solve the problem. So that's what we mean by variety as the characteristic of big data. All right. Now the fourth one is a little confusing to most of us. All right. So I'll start with a simple example. So veracity, when we talk about V for veracity, veracity essentially means, just because we do not know much about data we do not have a concrete decision on our data. And because of this unknowingness, or because of this confusion, we end up having a lot of data. Then we call that, due to veracity, we are having a lot of due to veracity, our data has become big. Now let's take a case. Say you are trying to do some kind of analysis on temperature. Okay, so you have got one data which contains temperature of all the locations of the world at every GPS coordinate. Okay, you have got a data on every GPS coordinate on Earth. Now that is one data. Now the second data you have got is based on the zip code. Third data you have got is based on your based on the city level. Okay, or based on certain other parts. Now when we have these three sets of data, we'll have to figure out, should we keep all these three data sets, or should we just delete one of these data sets, or just keep one of the data sets out of three. So till the point we take a call, till the point we make a decision that this data need to be kept and this data need to be deleted, till the point we reach to that conclusion, we will have to store all the three data sets, right? All the three data sets. And therefore, because of this unclarity or this decision which is pending, we end up handling all the three data sets. And this kind of cases where we, just because of our unclarity of the data and unclarity of decisions, we end up having a lot of data. We call this as veracity. Okay, so veracity is another characteristic of data, which makes it a case of which makes it a big data. All right, is this clear to everyone? Okay, great, great. Any questions till this point? All right, so just to check whether you are awake or have slept off, my question to you is, how many bytes are there in 1 petabyte? How many bytes are there in 1 petabyte? Satyanarayan says that it's 10 to the power 12. 12 is a gigabyte. All right. Okay. 10 to the power 18. Karthik says 15. Saiket says 15. Okay. All right. All right. Good. Good. So most of us, you are saying there is 10 to 12, 15. Good. Great. Now, yes, you're right. So it's 10 to the power 15. And the way you can remember it is using this table: kilo, mega, giga, tera, peta, exa, zeta, iota. And the fact is that why we are talking about petabyte or exabyte, because it will become quite common to handle that kind of data. It will, and it has already become quite common to handle that kind of data. We all are handling terabytes of data every day, and going to petabyte is not a big deal. So it is important to basically know how much data is how much. All right. So to feel that what does it mean by a terabyte, we will talk about few more problems today. All right. So that you get a feeling that what does 1 terabyte signify to us. Right. Now, hope this is clear to everyone. All right. So now we know what is 1 petabyte data and what is big data. Right. Now we know what is 1 petabyte data and we know what is big data. So can anybody tell me that is 1 petabyte data you consider as big data? Do you think 1 petabyte data is big data? Yes or no? Or let me rephrase my question. So you got 1 petabyte of data, you got to store it somewhere. Now, this storage need to be reliable, and every day we are going to increase this storage. So do you think handling 1 petabyte data is a big data problem? All right, because 1 petabyte means 10 to the power 15, and and a big data means not 15, it is 18, not 15. Okay, sorry, it is 15 only, because 9 is 10 to the power 9 is giga, and 10 to the power 12 is tera, and peta is right. So you have got 15 zeros after one, that many bytes, and a byte represents 256 states. Okay, your on off switch states, two on off button represents two states, on and off. That's a memory. All right. So if you have 10 to the power 15 switches in the world, how many how many how many states can you retain is what is represented by this amount of storage. All right. Now a big data is something, for I mean in very simple words, when you need multiple computers to handle a data, then we call big data. So question is petabyte a data for which you require multiple computers? All right. All right. So most of you have said yes. Okay. Okay. Most of us have said yes. And okay. All right. So yes, 1 petabyte data is big data, right? Because the existing systems to handle data, large data, cannot handle 1 petabyte data so easily. You might have to build your custom solutions to handle 1 petabyte data. Therefore, 1 petabyte is generally considered as big data. All right. Now, this is a classic diagram. This diagram basically shows the growth of data over a period of time. So few points here. The upper part is actually the analog storage, the colored one. It shows from left to right how did the data grow. So analog, the thickness of that strip represents the data at that year, right? So analog has not increased much. And what does it mean by analog? Analog could be paper, analog could be film, analog could be audio tape or vinyl, and and those old put I mean, all right. So old analog videotapes also, those are part of the analog storage, right? Now the digital storage, if you see, it has suddenly exploded. It just started increasing suddenly nearby 2002. Okay, 2002. So as you can see, the data has grown exponentially after 2002. And what does it mean by exponential, by the way? Exponential means the rate of change of something is directly proportional to the current amount. So when we say rich gets richer, okay, rich gets richer means change of richness of a person is directly proportional to the richness they have right now, right? So this is an exponential graph. If you integrate it, it is an exponential graph. Similarly, this data is an exponential graph, which means that the data which we are generating is somehow dependent on the existing data, and which is fairly true. So so in 2002, the data suddenly started increasing at such a fast pace that by 2007, as per the study, the data became in 280 exabytes. 280 exabytes, which means 3 followed by 20 zeros, right? 3 followed by 20 zeros. That's the kind of data it was in 2007. Now, given the same graph, if you plot it as of today, you will reach to yottabytes, zettabytes, and whatnot, or maybe far beyond that. So that's the state of current digital data. So as you can see, the data is growing at an exponential rate. An exponential rate is actually pretty horrible. When you draw it on the paper, you will realize that exponentially the data grows so fast that we cannot generally estimate it, right? So and this 2002 is called a digital age. And why did that happen? Why did that happen actually? The answer is twofold. First is the devices, second is the connectivity. Okay, devices and connectivity. Those are the two reasons why this data started growing really fast in 2002. And what does it mean by data? The data which is being gathered and stored in various devices at any point of time. Okay, so there were two main reasons. One is devices. Every device manufacturer, whether it is IBM or whether it's Sun Microsystem or any device manufacturer who has been, even Motorola and everybody, their sole aim and the sole KPI, key performance indicator, or their sole objective of every product design is to build a hardware which is cheaper, faster, and smaller. The computing device, the objective of a complete computing device is to become cheaper, faster, and smaller. Those are the three objectives, and they have been fairly successful in delivering that. As of today, we have a full blown computer in the form of a very small handband. That is the state we are talking about. Okay, so smartphone became so powerful that the phone which we carry around today is equivalent to the supercomputer that was in 2002. Okay, So in 2002, the same amount of that kind of power was there in the supercomputer, and we used to think about. I mean, we used to use that. You use that kind of computing only in sort of, you know, the world changing problems such as finding the I mean, do a DNA analysis and do a various kinds of research and analysis. But today we use the same kind of computer sitting in our pocket to play Angry Birds. All right. So and that's the state we are in. That's the state we are in. So the devices are growing cheaper, faster, and smaller, and the connectivity has grown faster and faster day by day. And as of today, having a 30 mbps is not a big deal. So there are two things: connectivity and this. So because of connectivity and the devices, the softwares was built, and we have an ample amount of softwares available today to do everything what is required. Okay. So basically, these are the reason why the data has grown so much and is growing every day. All right. So it shows me that my connectivity is down. Can you hear me clearly? All right. All right. So good. So when we talked about connectivity improved, it dropped my connection. That's irony. All right. Now, now when we talked about how the data is growing, we talked about why the data is growing, and now I'm talking about why this growth of data, which need to be handled when the data need to be handled, or due to the growth of data, we have big data in place, and when we handle that data, what kind of challenges it portray. So before we say that the on the hardware level, let us broadly look at what kind of things are there in our computer. We all know it, but let me just say it again. So first one is your CPU. CPU is the main component in your computer which reads the data from RAM and writes back to the RAM, or writes back to the disk, or writes back to the network, and vice versa. All right. So CPU's job is to read instructions, execute the instructions. Okay. Read instructions and execute the instructions. And a number of instructions it can read, or number of decisions, number of flip-flops it can do per second, is known as the CPU speed. Okay. Processing speed. Now every now and then, all right, so we have got CPU, which basically, the faster CPU we have, the better it gets. But CPU is not the only thing which matters. You might have a brilliant CPU and still you may not be handle the data. The second one that bothers us a lot is the RAM. The RAM is basically, processor reads most of the data from the RAM, random access memory. So generally, reading writing from RAM is fairly fast, but still the read speed from the RAM matters a lot. Therefore, this RAM is an umbrella term I'm using. It represents L2 cache, L1 cache, and other registers also in this definition. So the speed at which you can read from RAM and the speed at which you can store to the RAM also matters, other than the size of the RAM. So mostly when we are dealing with servers, say you have got a high throughput server, although it's a static website of 5 MB in size, when the velocity grows to your website, when there's a lot of connections keep on coming, just to handle those kind of connections, your web server would require a lot of RAM. All right. Your single computer will keep on requiring more and more RAM, and there'll be a time when if still the connections are growing, you might end up with 200 GB of RAM in that computer. And if it grows further, you will say that we cannot handle this amount of velocity using this single computer. We need to install the same software on another computer, and we need to divide our traffic into multiple nodes, and we need to build a software which can run in this distributed fashion, right? And that's what we call that. Because of the limitation of the RAM, we ended up having a distributed architecture. So a big data impacted our RAM. It was not physically possible to have a RAM of, say, 2 terabytes. Okay, because the biggest, I mean, it's not possible to have 2 terabytes of RAM and still function very well, right? So CPU is, of course, when you have a problem which requires so many computing cycles per second, say your processing is taking too much time, just processing, then you might require a multiple computer. So when the CPU becomes bottleneck, then you require multiple computers. You could, that's the only way you go forward. And there might be a scenario when you cannot store everything in the RAM, so you will try to store it on the disk. And sometimes the data is so big that you can't store on a single machine. You will single disk, you put it on multiple disks. And if you, after beyond a point of time, you cannot store it on a single computer, you cannot connect more disks onto a single computer, then you will store it in the network. And that's how the whole process grows. So any of these four components, disk, network, CPU, RAM, will become your bottleneck when you handle the big data. No matter what you do, no matter how you, when we code, when we try to build things like we build cache, we build a cache, or we build something else, we build a disk supported page faults, right? Paging is nothing but moving the data from RAM to the disk, right? While caching is the other way around. We are moving data from the disk or the network into the RAM. So we keep on moving this data back and forth between RAM, disk, and network, just to handle this kind of data. And there is a point where your network, disk, RAM, or CPU becomes a bottleneck, that you say that we can no longer increase any of these four things. Okay, we can no longer increase the CPU beyond this limit. We can no longer increase the RAM, and we don't have a network card which can read the data faster than this. That is the time you say that let's have a distributed computing system. Okay, let's have a distributed computing system, and rather than transferring the data, let's send the logic to the data. We'll talk about this part very quickly. All right, so this is clear to everybody. So at least one of these components will become the bottleneck for you. All right, great, great. Any questions on this so far? Any questions for me so far? If you don't have questions, there could be two reasons. One is I have put you to the sleep, or I am so great that I explained everything very well. There is no doubt left. Yes. So Chetan, that is the kind of definition we carry with the big data. All right. Should I carry on? All right. So these are very few example use cases. These are based on few example customers, but the use case is far beyond what is there in this slide. The use case is far, far, far beyond. All right. So this is just the very small section of the problems being solved by using big data solutions. Okay. Big data customers, as in big data customers of the big data solutions. All right. Now here, the first one is the retail, web and retail. And out of it, probably the recommendation engine is the most common one you will see. And the recommendation is the one which will basically give you quickly which will quickly make you realize the importance of big data. So what is a recommendation engine? Anybody? Or give me just a quick example of a recommendation engine where you have seen it. Just any one example. Yes. TripAdvisor, Flipkart recommending similar products while buying one. Excellent. Excellent. Yep. So recommendation engine by definition is quite straightforward, whereby given your a little bit history about you or little bit information about you, if a software or a person is able to suggest you something based on your kind of a history, is called recommendation. Okay, me and you meet up, and I say that, I like this movie, I like this movie, I like that movie, and you say, oh nice, I too like those movies. So then you start recommending to each other, have you watched this, have you watched this, do you may also like this kind of movie if you like these movies, right? So that's a kind of recommendations which have been there for maybe thousands of years since the people started talking, right? So those are the called generally the recommendation engine. Now when it comes to the big data, so why does it, when recommendation is there forever, and recommendation is not something which was invented by this kind of computing, it was there was statistical analysis all the time. Okay, statistical analysis all the time, like saying that the people in your geographies do this kind of things is actually a recommendation under the hood. It's a silent recommendation telling you that, hey, what, people in your area are actually, liking these kind of products, why don't you also try this? So that's a kind of a recommendation people are trying to do. Now why does it signify, what does it mean by having recommendation engine as of today, right? So when we talked about me and you meeting up, we first understanding how similar we are, and then we are telling you that if you like this movie, you will also like this. That's a product to product recommendation, and user to product recommendation is basically based on people who liked this movie. I mean, sorry, there are these users who are similar to each other, and therefore this is what they liked. So there are many kind of recommendation. The most important part out of it is, more the data we have, the more the data we have, the better will be the recommendation. When I say better will be the recommendation, first, the better recommendation means you have more precise of data. Meaning, when I say that, hey, you might like this movie, and you go and watch that particular movie, you say, yeah, you were right, I actually like that movie. So that is called a very precision in the recommendation. Now, second point in the case of recommendation is, I should be able to give you more recommendations than one. Okay, it should not be that though my recommendations are very precise and they are very effective, but I have given recommendation only to few users, and I have given them recommendation of few products. So we need to fine tune, and we need to grow the data, and the more the data we grow, more we will have more things to recommend to you, as well as we'll not have to compromise the precision of our recommendations. Why? Because we have data. So the more the data you have, the better your recommendation gets. And that is why big data always makes a use case for big data always makes a use case for recommendation engine. Yes, you are right, Satyanarayan. That's exactly how it is. So the bigger the data, the more correct will be the analysis. That's exactly what which is correct. Even if you have to compute the average height of, say, of people in this in Bangalore, if you have just three people whose height you could measure, and then say, average height of people is this much, right? So your sample set is quite low. The bigger the sample set, the better your computations and analysis goes, right? So that is why recommendation engine makes a standard use case of big data, right? The other reason for recommendation engine is that there has been hundreds of algorithms, and there has been a humongous research in the field of recommendation engine, so that all of these algorithms are available in open source to everybody. Even the algorithm which won the prize recommendation prize in last year is available in public domain, right? So that is why when you have all the tools available, why don't you generate the recommendation? Then what stops you? The only thing that stops you is, first, you don't have data because you did not bother to store it. And why did you not bother to store it? Because you did not build enough amount of storage so that you have no worries of storing the data. You have no mental block whatsoever of storing the data. If you build that kind of storage, then you will be quite rich in terms of giving the recommendations, right? Now, the second one is ad targeting. Okay, so I'll skip the ad targeting part. It's basically finding the right match for the ad which is being displayed. I'll talk about search quality because ad targeting is very specific to few candidates in industry. There are hardly 50 people in the AdWords. There are hardly 50 players in case of advertising. Now that's why let me talk about search quality. Now search quality is not about building another Google search. Search quality, when I talk about search quality, it means a simple search engine for your intranet, simple search engine for your own product. Okay, say you are a small e-commerce company, you have got hundreds of products, or maybe say 1000 products, and all you want is you want your user to be able to search very effectively. All right, now, and how can you improve the search results? First, building the dictionaries. Okay, second, by correcting the typing mistakes, right? And by building an enormous amount of auto suggest corpus, right? So first thing is that based on the data which is available on World Wide Web, say you have everyone, me, you, and everyone have access to the Wikipedia's data as of today. You can download the whole corpus. Now, based on Wikipedia's data, can you figure out what are those two words that always come together so that you can give the recommendation to the user when they're trying to search something? Second, based on the data of World Wide Web, if we can figure out that this and this word is always used interchangeably, in the same context, right? Then then when people searched in my system, I will all if you search for a search for say T, T-E-A-T, I will give you the results of chai also. CHAI chai, because I know that chai and tea is used interchangeably across the globe, right? So if we can figure out this kind of a corpus of the data from World Wide Web, then our results will be really powerful, will be really more effective, and users will not complain, right? Now, you might argue that your system, your learn say you have built some recruitment management system, information management system, help desk. I'm sure every company has built these kind of solutions in their organizations, right? So though though you might argue that you haven't, and you don't want to, but my understanding is everybody builds kind of information management system at every point, at various points in the software development cycle. Now, and even though the data you are storing in your recruitment system, in your MIS system, the data you might be storing might be in few GBs, but just to provide a good search, just to provide a good search, you might have to handle lot of data to build your dictionaries, to build this information that chai means tea, right? And when people search for say shirt, say Levi's, when people search for Levi's, your search engine should know that the user is talking about Levi's as in jeans instead of Levi's, some book on Levi's, right? So that kind of understanding, to develop that kind of understanding, you might have to churn a lots and lots of data, right? So all I'm trying to portray is the excuse which we give that we don't have that kind of data right now, and therefore this big data doesn't matter to me, is false, right? You might have to do a lot of phonetic search because your customers, their expectations have grown higher. They have seen the systems like Google, they have seen systems like uh, Gmail, they have seen systems like Amazon, where you put a word and it shows you the results. So it becomes inevitable to build a search quality. And why I'm emphasizing on this point, because I have seen it. I built a simple document system which was essentially data in and data out, but after a point of time user said that we need a search engine, we need to find our document. Those days are gone when people used to categorize this stuff and then organize it very well, label it, and then you expect people to find it by themselves. Those days are now gone. You need to provide the search. There is no other way out. All right. Therefore, search quality is must, and hence the big data is needed. Fourth one is something called sentiment analysis. This is also very popular and public problem. Everybody is having a sentiment analysis as of today, right? Even a small company, small brand, big brand, everybody does sentiment analysis of their products, their competitors, and what are they, and all sorts of things they need do a sentiment analysis upon. Okay, and how is sentiment analysis done? I'll just give you a very brief example, and then we'll go into in the ninth session we'll go into the details about what does it mean by sentiment analysis. Okay, sentiment analysis essentially means that you take the data from public, you figure out whether a sentence is negative or positive based on your dictionary that contains the meaning of each word in terms of emotions. That say, when I say bad, it means it's a negative word. When I say good, it is a positive word. When I say nice, it's a positive word, and so on. All right. Not is a negative, yes is a positive. So there's a huge dictionary available to understand the words. Yes. So pre-poll survey does come under this, but generally these surveys are, I mean, yeah. So surveys do constitute too big data in terms of velocity. Here, sentiment analysis is post one where you already have a lot of data and then you do it. Yeah. So sentiment analysis is generally based on, instead of polling, it's based on figuring out what is people's response. Okay, because in poll you conduct the polls and then you do that, right? And in sentiment analysis you just observe what are people talking about you. Okay, so there is an audience standing in the playground, right? If you can capture what they are talking about and then you deduce that people are, I mean, our people are talking negative about your brand, then that is sentiment analysis. Though, and if you go with a mic and camera and then or you go with a survey form and ask all of these people to fill that form, okay, so the results are going to be different in both the cases. Okay, as an example, if you build a survey to find out terrorists in the world, all right, and you build a, in this the first question is, are you terrorist, and you send this form around, and the conclusion of this poll will be that there is no terrorist in the world, because everybody said no, I'm not the terrorist. So say question was, are you a terrorist? The answer is no. So based on the poll we will conclude that there is no terrorist. All right, so so that's the difference between polling and doing a automatic analysis. In case of sentiment analysis, we download a lot of data from various forums and what are people talking about us. Okay, and say Twitter, say you have just now given a public speech, and are people talking about you? How many people are talking about you? If there are say 10,000 people who have tweeted just now about you, you figure out that this is negative or positive. All right, so I hope I am able to give you a thought clarity. All right, so let's take a 10 minutes break and come back at around 3:38. Okay, and grab a coffee. All right, yeah. See you then after 10 minutes. Bye bye. Hello. Yeah, I'm back. Are you guys back? Should I start? Should I start now? Hello, can you hear me? Hi, is my voice audible to you? Hello? Hello? So are you guys back? Should I start now? Hello? Okay. All right then. So I'm starting again where I left off. Great, great. Thank you, Gayatri. Thank you, Chitra. Thank you, Karthik. And here we go. All right. So, then the fifth point, we talked about sentiment. Is sentiment analysis clear to you, or should I explain again? Is sentiment analysis clear, or should I explain again? Yes. Okay, it's clear to. All right, all right. Thank you, Chaitra. So let me give one another example to explain what does it mean by sentiment analysis. So let's say a movie which was getting released recently called PK, and the movie was getting released. Before that, they did a lot of advertisement. So the one of the stick to measure how is PK doing, and would be to download all the data from Twitter. So find all the data which contains the word PK from Twitter, download all the such tweets, then for each tweet find out whether the tweet is negative or positive. This is done by looking up each word in a sentence and then summing it up. And after that we know that these many people are talking negative about the tweet, about the movie PK, and these people are doing positive. So once you have built this system, you do it every day and you plot a graph, various kinds of graph, which shows that these are the kind of people who are not liking PK, This has been our performance before the movie was released and after the movie was released. If people were talking positive about PK before the movie was released and then suddenly people started talking negative, that means movie is performing really, really bad, right? So that kind of an analysis, or say one particular great leader is giving his speech. He wants to understand whether I gave a great speech today or I gave a bad speech. So the general stick to measure is that we do the analysis about that particular leader before and after the speech. All right, and then we measure whether people talk about him in a positive manner or negative manner. All right, after the speech. So these are few examples of sentiment analysis. Right, right. So the other cases are abuse and fraud detection. And for that, mostly in case of a fraud, we do not really know a general pattern upfront. Okay, so as and when we go see more and more cases of fraud, we form a pattern. Say for example, whenever somebody is somebody is buying a lot of things on his credit card suddenly, that means there is some fraudulent activity from on this card. This is generally so if a certain budget, if a particular purchase becomes sudden and becomes very, very high in quantity, then we generally say that it's a fraud. But that's not the only pattern. There are multiple kinds of different patterns. Say one credit card was tried from two different locations at a gap of few minutes, one from India, other from US. Okay, so what could be the reasons behind this? Maybe the person changed the proxy. Maybe there are two people having the access to the credit card details, and so on. All right. So those are the patterns which are basically detected when we talk about uh, abuse and fraud detection. Now, there are other kind of things which people are. These are the things I'm talking here. These are the most popular use cases across the various kinds of industries. So the things which I've talked about is web and retailing. Now, in the telecommunications division, the telecommunications vertical, lots of innovations happen. And these days, most of these innovations revolve around big data solutions. So these are four use cases where big data or Hadoop is being used as of today. And this one I have taken from Hortonworks website as the use case. And these are the places where Hadoop is being used. All right. Now telecommunications and why I have taken from only Hadoop, because uh, other data was not readily available to me. All right. In case of telecommunications, the service provider has all the details about the user, including who the person called last time, who the person called yesterday, and so on. All right. As well as, so based on the past behavior of the user, if we can figure out why did a user leave us, then we can also figure out how can we retain this user, right, before they leave us. So we will analyze how many calls were made by this person to various our customer representatives, or how many emails were sent, what was his signal quality for last 1 week, and what has been his expenses, how much did we charge him. So based on all of this information, we can figure out why did customer leave us, because those days are gone when we used to force our leaving customer to fill up a survey. Okay, those days are gone because that survey was never correct. You might ask your user that why are you leaving, they might say something, but the real information you can get only after observing the user, right? So for customer churn prevention, big data is being big data is being churned, big data is being analyzed, and there are many big data solutions that are in place into such kind of use cases. Then second one is network performance optimization. To you can optimize the network performance if you do the fingerprinting of the whole network. Okay, so for example, if I do the fingerprinting and understand that on except for holidays, except for holidays, all the people generally go to in the during the daytime, most of the people move to the to the to the ITPL or electronic city or similar area, so the density of people increases in these tech parks. Okay, therefore we need to increase the capacity and the signal capability in the areas having the technic tech parks, and the pattern is this much. So based on lot of fingerprinting of the data, we can do a network performance optimization so that our users are very happy. There are hundreds of similar use cases which you can come up with for your own customers and can say that, hey, can we do this for our customers so that they are more happy than now? Okay, and most of these decisions are based on the data you have. All right. Then there is something called calling data record analysis. Based on your calling data, there are many kinds of insights possible, and these companies do that. All right. And figuring out where is the, like for example at Amazon, one of our projects was to do the prediction whether today this user is going to buy or not. Okay, so we generally used to do this kind of analysis, that as the user logs in, how much is his decisiveness. If his cursor movements are faster, if he is clicking really fast, he's he has put in a keyword properly rather than browsing for something, or he has come directly to a product page. Okay, so based on all of this analysis, we used to say the confidence that this user is going to buy today. All right, and what has been this user's past history? Okay, based on all of that, we could predict fairly confidently that this user is going to buy today and this user is not going to buy today. Okay, although this statistics was of not much use right at this point of time, but still we were able to predict at a very high precision that this user is going to buy today. All right, so so basically those kind of interesting things could be done if you have good enough data. If you have good enough data, you can actually do a lot of uh, analysis and come up with various use cases. All right, similarly governments and healthcare and life sciences uses big data, and they are using it, they are not something futuristic. All right, and this is the general slide where number of Hadoop instances are represented as the font size. So bigger the font size, more number of Hadoop instances are there. So Yahoo has maximum, then is Facebook and LinkedIn, and then other companies. Okay, but there are so many companies already in the game. All right, now any questions still here? Now, there are few common myths about big data. First one is always Big data always means data above or in range of terabytes. No. Even if data is smaller, you might have to use a distributed computing platform to solve your problem, right? Second is, big data is always about social media. It doesn't apply to me. No. As we talked about various kinds of problems, you will figure out that this is not true. Third, it will replace EDW. EDW is enterprise data warehousing, right? So enterprise data warehousing has got its own use cases which are really good. So EDW will not be replaced straight away by Hadoop, although some of the parts will move to Hadoop, okay? Because enterprise data warehousing is for more real time and more transactional data, while in Hadoop or any of these big data solution, in case we try to do transaction kind of transactional analysis, it will be very difficult, okay? And that is the reason why no transaction support has been provided in most of these solutions, okay? Is just a buzzword, no practical application? No, it is very popular. I mean, I agree that it's very popular, but it has got real practical applications. It is not just a web 2.0 kind of thing. Here there's a huge technology platform, and this is not something which was done in one day. It has been there since ages. I'm telling you since, because I have been working on this kind of platform since 2002. Although those platforms were local to the company, they were our private platforms. There is a lot of things, you know, lot of practical applications were there. It's just that it has become clear to general other companies also that big data is quite useful to them. They can also build really cool stuff using big data, okay? And they can also, if they can handle that kind of data, they'll be able to do various kind of analysis, and therefore they start storing a lot of data. It's just a new concept? No. Will be the future? No, because it's the present. All right, it is the present, it's not the future. Is expensive? No, because almost all the tools are open source and available, okay? And documentation forums, because these tools are available, so lot of discussion is available on each and everything. Every time you get stuck on any of the tool, you can just go to Google and ask. None of the documentation is proprietary. All right, is for data scientist or is magic? No. Data scientists, whatever data scientists play the role, that is available in the form of libraries. There are various kinds of Java library, Python library, this, that, and it's available there, okay? So whatever data scientists do, most of it is available in the public domain, which is open source, and you can use it. And that makes it, that makes it, make sure that it's no longer a magic, okay? We have enough hardware, doesn't need it, not don't need it anymore. So the thing is that it's not about hardware, okay? It's not about hardware, first. Second, the hardware most of these solutions use can be very low end. Even if you have a few years old computer which has got a decent amount of RAM and hard disk, you can start using that one, okay? And almost all of these solutions are built bottom up, thinking in terms of the commodity hardware. You should not always be buying blade servers for all of your data center. No, you can actually have a decent enough hardware, and then you can use that, okay? 10th common myth is we will build it when we need it. That's completely absolutely wrong. Why? Because tomorrow you realize that, hey, we can give the fantastic recommendations to our users, and now all we need is that we gather this much amount of information about our user of past 10 years. Now we cannot go back to the past and start gathering information, right? So That gathering of the information should have been done 10 years ago or 5 years ago, right? Therefore, therefore, you cannot always say that we will do it when we need it. You need to start doing it now. And to do that, you need to build the capability of being able to store hundreds of terabytes of data so that all of your developers who are going to store logs, who are going to store the user behavior, where did the user click and what did the user do, all of that kind of information need to be stored. Only then only then you will be able to do the analysis at later point of time. You cannot go into the past and change the past, no, right? Therefore you need to start now to start building it so that when you need this kind of analysis, it's there always. Okay. Big data is always about Hadoop. No, there are many other solutions such as MongoDB, Cassandra, independent Cassandra, as well as there are many other kind of solutions which which target the big data. All right. Hadoop seems to be the most complete solution. Great. All right. So let's just jump on to now Hadoop. Okay. All right. All right. So Hadoop was created by somebody called Dog Cutting and Mike Caffarella. And can anybody tell me that what was the name of the Google's component on which the Hadoop is based? What are those papers? The name of the components on which Google. So Google wrote two papers and made it popular. One is MapReduce. Good. Thank you, Vishnu. And the file system? GFS. Excellent. And third one? The one from which the database is inspired, HBase is inspired? Excellent. That is big table. Great. Great. So basically, Dog Cutting and Mike Caffarel, these guys were working at Yahoo, and they wanted to build their own search engine just as a hobby project, personal project. And and that's when they realized that to build a search engine you need to first gather the data, and to gather the data you need a place to store the data, and to store the data you cannot do it on your normal disk. You need to build a solution which can utilize multitude of computers having multitude of hard disks, right? And therefore they built Hadoop, and they also tried to build Nudge. Though Nudge wasn't greatly successful, but Hadoop is greatly successful. Now, for Hadoop is open source Apache, which means that you can use it in all the in your personal project, training project, or even in the production environment without having to worry about buying the license. You are not doing anything illegal or wrong by downloading and start using it right away, right? So that makes it possible for any Apache licensed software to get the wide adoption across the globe, right? That's probably one of the reasons why every new system is open source, and that too under Apache license, because Apache's license is probably the most accepted license and is most liberal license available today. Okay. And the point number G on this slide, and F and G. So after a point of time, Hadoop became a platform. Hadoop became the bundle of components. Hadoop did not remain only those three components. One was initially they built first one as file system where you can store a lot of file. Then they built a computing engine on which you can do a lot of computation. And third one was HBase. These all three were based on Google's Google's paper on a similar things. right? Now, after a point of time, Hadoop became a bundle of component or a platform or a top level project at Apache, which has adopted many small projects, right? So all of the projects which Hadoop has adopted, as of today, there are around 15 components which are under the umbrella of Hadoop. All of them share a same characteristic. All of these components are the frameworks to handle big data. All of them are built, are reliable, scalable, and for distributed computing. Okay, reliable, scalable, and distributed computing. So any software which wants itself to be adopted to Hadoop suite of components, they need to be that software need to be reliable, scalable, and distributed. All right. And the last point, probably the most important point, is Hadoop is written in Java, which means that it can run on multitude of computers. Even these computers might be having different kind of operating system. So theoretically, having HDFS running on Windows on one machine, another machine being on Unix, another machine being on Linux, they all can work together very well because Java is has same implementation across Windows or on Unix. All right, and that is the reason that we have HD Insights, which is basically Hadoop running on Windows. The same Java code which was running earlier on Linux is now running pretty well on Windows and is available as part of the Azure services from Microsoft. Sounds good to you? Now, let's have a look at what are the components which are there as part of the Hadoop ecosystem. So, we have these components in general. Do you see that? Now, we have got the most important one out of it is the file system. File system is one where we store the data in unstructured form, which is a file, and then we just take we talk in terms of the file, right? We don't talk in terms of records. So Hadoop distributed file system is what is the basis of all the systems, and all of the other systems actually are built on top of Hadoop distributed file system. Okay, so now let me dive deep into Hadoop distributed file system, and before I move on to the file system, let me talk about a very simple thing to you. Say in your organization you need to have a space of 1 terabyte. Okay, you want to store all of you guys, say you are say 300 people, 400 people in your organization, or maybe 1000 people. What you want to do is you want a common place where you can store your data, and this data is going to be 100 terabytes. Okay, now we are not talking about permissioning. Let's say we are going to store something like videos or something like that, where let's say we are going to store all the movies. Okay, we're going to store all the movies so that our whole organization can watch movies from this place. All right, now as per our random calculation, we realize that over next 1 year we might need around 100 terabyte of storage space. Okay, so how would you build it? How would you build this kind of storage space? Okay, or if you have 100 terabyte of data, how are you going to store it? It's the same thing. How are you going to build 100 terabyte storage space? Anyone? Feel free to answer this question. This is a very important question. Okay, in multiple memory. Okay, how? How will you build that multiple memory? You mean to say hard disk, right? We are we are talking about 100 terabytes. So how will you use? Good. Karthik is saying that what you do is distribute it on multiple systems and share it as a network drive. Excellent. Excellent. And okay, Pratik says by dividing data. Good. Good. So let's say we will. Okay, okay. I'll give my solution later. I want to see your solutions. Good. Any other, just anything what comes to your mind. Say it's a genuine problem. You have got you have planned that you will have 100 terabyte of movies or videos which the whole organization wants to watch. Or you are living in a society where there are hundreds of thousands of people, and you want to build a movie storage from where everybody can watch the movies. Okay. Ramya says network file system. Good, good. And good. Satyanarayan says that it should have similar internal mechanism which OS uses to allocate and track memory for an object. Great, great. So what does it mean by Satyanarayan? So he says the way we are managing the local on the local file system. On local file system, we have something like a file file system header, which stores the information about where where is the data stored, right? How big is the file? Where is the things stored? And accordingly, accordingly which file is stored where is located on the initial part of the file system, and we can look it up. Good point. Very good. So we'll utilize this bit of information when we are building it. Okay. Anybody else? Vishnu says in the cloud storage. Good. But here what we're talking about, you are the cloud. Okay. You are the guy who is responsible to build such a cloud. Okay. Because I mean, you are the cloud engineer whose responsibility is to build that kind of thing. Only difference is that we need to keep track of IPs where data is distributed. Excellent. Excellent. So what his point is, the way on the local hard disk we have these pointers saying that this is where our data is stored for this file. In the header we store all the names of the files and where actually the data is stored. So whenever we find a file, whenever we try to read a file, we first go to the file system header and see where exactly is the data of this file located onto the drive. All right, that is very good. So what he's saying, that instead of talking in terms of the address of the file system, we will be talking in terms of IPs. Very good. Okay, good. Any other ideas? Good, 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 good. Any other ideas? How are you going to build 100 terabyte storage? All right. So exactly on the same point. So Satyanarayan is actually pointing to the final solution. We'll talk about his solution when we talk about HDFS, and it's a very good point. Good. So the way you guys have said, some of us, that what will you do is you will basically build a network file system, or we call it network attached storage or storage area networks. All right, and that's what we will build. Now what does it mean by them? It means that we'll buy a lot of hard disks. hundreds of terabyte of hard disks. And we connect these hundreds of terabytes of hard disk, 101 terabyte hard disk, 100 hard drives. We connect these 100 drives to say 10 computers, and all these 10 computers are having 10 hard disks each. And now we have bingo. We have 100 terabyte of data, right? And once we have attached these hard drives to these physical computers, we mounted these hard drives at a single point so that, see, what does it mean by mounting? Mounting means that when you look at the main folder, you will think that each hard drive is just like a folder. In this main folder where you have mounting these hard drives, these hard drives will look like a folder to you. All right, that's what is meant by mounting. Now, every time you double click the drive 1 and try to store things, it goes to the hard disk 1, no matter where is it stored. And this is how we had been doing things for years. This is how we had been doing things for years. Okay. Now, so is this diagram clear to you? We took a computer, we created a folder on it. Then under this folder, we mounted, we linked each hard drives available in the network to each folder. Now, whenever and when we are trying to store the data, we formed a scheme such as all the movies starting with A will go to drive 1, all the movies starting with B are going to drive 2, and so on till the end. All right. Now, do you see any problems? Do you see any problem with this kind of architecture? Or this is perfect for you? Do you think that for storing 100 terabyte of data, is this good enough? Okay. Okay. Great answers. Yes, lot of hardware, good. It is very data specific. Okay. Okay. You mean to say that when we say all the movies starting with A go to drive 1 and so on? Yes, you're right. Yeah, you made it clear after this. So if we have more of the movies starting with S, then only few data storage will be used. Very good point, Satyanaran. Good, good. Okay. Drive failure leads to the data lost. That is Karthik's point. Good. So imagine that the way we had been doing in the olden times, what we will do is on each computer we will have another hard disk keeping a backup copy of the existing hard disk. So if a computer has 5 hard disks, so we attach 5 more hard disks to it, and those 5 hard disks will be used as backup. Do you think it's good enough? So effectively, we'll have 200 terabyte of storage, out of which only 100 terabyte is being used because 100 terabyte is just for the keeping the backup. So my question to you is, do you see any problem with this kind of architecture? Yes. So data distribution is definitely a problem, Satyanarayan. That is not solved yet. Yes. Concurrent write and read. Very good point. Thank you, Karthik. Okay, we'll talk about this. Concurrent read and write, as in if people, while one person is writing the data should be accessible in some form to the another user, even if the another user is reading the older data. Okay. Any other problems do you see? Data integrity. Okay. Data integrity as in? Data synchronization, good. Any other problem do you see? So we have got these 100 drives in this folder, okay? And with each drive on each computer, we are also keeping another drive as a backup. Memory waste, okay? So you mean to say that the hard disk space we are only utilizing 100 terabyte out of 200 terabyte? Or you mean to say that even even though we have built 100 terabyte of space, we may not be able to store all kinds of movies, all sort of big, all, the whole 100 terabyte of movies. Okay. Any other points? Poor storage management. Yes, yes, that is true. That is true. Okay. Go ahead. Yeah. Do you think any other problem with this? There is a chance of failure of the backup node as well. Very good point, Pratik. Great. I've got great solution, great points from you. Any other do you think? Great. What if storage having main folder goes down? Yes, that is also very much possible. Good. So remember, this main folder does not contain anything. It is just showing these links, which when are clicked, take your data to that particular drive. So the only thing the problem would be that where will you find these folders? Yes. Good. And anything? These are very good questions. Okay. All right. All right. So, yes. So, think of this list as what you have written, but in my words. Now, the challenges and the problems which I foresee, and I mean, the challenges which would occur in this kind of scenario. First one is the failover and backups. Okay. What does it mean? We talked about backing up each hard disk, but hard disk failure is just one kind of failure. There could be a network failure, right? There could be a network failure. There could be system gets corrupted so that OS is no longer available, and that's not something very improbable. That happens all the time. So our failover and backup is not really available over here. Failover as in even if hard disk goes down, there should be somebody else where the data is stored available. All right. Third, is this the best value for money? Is this the best use of resources? Because you might already be having a lot of hard disks, and can you utilize those? Is it possible for you to utilize those? Next one is, how would you distribute your data uniformly? Okay, we talked about these hard disks. What if drive 1 has only half GB left and you want to store and your files are 1 GB each? Drive 1 only has half GB left and all your file are minimum of 1 GB size. Now this half GB is going to be empty all the time. Or look at it this way, drive 1 had 5 GB left as the storage, and you have 5.5 GB of file. Now you cannot store it. That means your whole plan is going to go for a toss. You will have to dedicate more servers for alphabet A or some other mechanism, right? Now, the next point, which is what about increasing accessibility? This is something very important. One of you actually told that this is right. Now, what does it mean by increased accessibility? So, a new movie came yesterday, and this new movie, say PK, it came yesterday, and we stored it on drive number 10 because for letter P, we dedicated drive number 10. Now, everybody in your neighborhood or everybody in your organization wants to watch that movie. So drive number 10 is going to get really overloaded because a drive a particular drive cannot actually handle two read requests at the same time. Why? Because the hard disk header is a physical instrument which moves forward and I mean which jumps to various places to read the data. So hard disk header can only read only only support a single request at a particular time, right? Therefore, this drive number 10 is going to become the bottleneck and is going to maybe burn down or go unresponsive or becomes unavailable. All right. As well, the network of the drive number 10, which is containing a movie which is in heavy demand, is going to become the bottleneck. The network is going to become the bottleneck, and so on, right? Now the last point is scaling out. Today your need is 100 terabyte. Few months down your need is 110 terabyte, right? So can you scale up? Can you every month can you keep adding few terabytes of uh, disk storage onto this solution? Okay, and still scale out is this. Scale up and scale out are two different things. Scale up means you increase the hard disk from 1 GB to 2 GB. You threw away old hard disk, you bought a new hard disk which is of a higher capacity. That is called scale up. Scale out is adding one more server next to your existing one in order to cater to the scale. All right. So, are you convinced with these all points, or am I lying for you? Do you think that these are the challenges, or these are just made up by me in order to sell you the HDFS? Oh, so you believe that? Oh, okay. Sounds, reasonable from my side. Okay. Okay. Good. Good. So the solution here is that you go for a distributed file system like HDFS. Now, we talked about 100 terabytes. When we talk about 1000 terabyte, which is 1 petabyte, the problem is going to be 10 times harder or maybe more hard than what we are facing now, right? So in those circumstances, we might have to build a newer file system. And what does it mean by a newer file system? We'll go into the details. All right. Now here we go. So somebody said, if Miss, I think Satyananand says that Okay. Satyanan said ki, just like we design file system, we need to build a similar way. Yes. Or you can think of it as that we build, instead of have storing this way, the way we are storing just now, what we did was we kept the index of which movies were in another file, right? We kept in this information about which movies were in another file, so that we keep on filling the data properly onto these hard disks, so that the drive wastage is very less. And that's how the HDFS is built. So an HDFS cluster has multiple computers. Whenever we say HDFS, we should not be asking that, we should not be asking that which processor is it. We should be asking instead that how many nodes do you have in your HDFS? Okay, that's the kind of question. So whenever we say HDFS, Hadoop Distributed File System, it contains multiple computers. And now these computers are there two kinds. First is name node, or known as admin node. One of the computers is dedicated as the master and is known as admin node or name node. This computer, it contains the index, the data, and the information about what is where. All right, that is name node. Now rest of the nodes in the HDFS clusters are known as data nodes. Okay, data nodes are multiple. They are the basic storage horses which contains the humongous space to store your data, right? So this name node basically is index of what is where, and what is where, which means it's a data over data, and data over data is known as metadata. All right. Now the data nodes store the actual content, and that's where your all data will be lying. Now the information about what is folder, which folder is where, all of that information is lying in the name node. All right. So this is clear to you. You have got admin node and data nodes. Admin node stores what is where kind of information called metadata, and the actual bytes of the file are stored onto each data node. And admin node keeps a track of which file content goes where. All right. So that's the first step. The kind of, you have index and the other information. All right. Now let's move on. So name node basically contains the data. Name node essentially contains where is what. Okay, what is where. And data node, each of these data nodes, you see these machine to machine 3, they are supposed to read and give the data to the user. Okay. Now next thing in case of HDFS is, when the file is being stored onto data node, it's broken down into pieces. Okay, just like we fill a jar with small bricks. Okay, we don't put a big brick into jar, we make it a small pieces and fill it, only then we can fill it. Similarly, each file before it goes for the storage on the data node is broken down into the blocks, and these blocks are of fixed size, generally of 128 MB. Okay, these blocks help you fitting big file onto small hard disks. Okay, why? Because say you have a Blu-ray which is 80 GB size, and out of 80 GB it will break how many? 640 pieces. 80 GB means 640 pieces. Why? Because 1 GB will be broken down into 8 pieces of 128 MB each. Now, if you want to store 80 GB, these pieces will be stored onto data node. Okay. Now, the basically when you slice the big file into a smaller one, there are many benefits you get. You are able to fit big file onto small disk, leaves less space left into each jar or each data node you can think of, because if the file each file was bigger, the chances of having the bigger empty jars is higher. Fourth is it optimizes the data transfer. If you have to rebalance the file, if you have to rebalance the file, so Karthik, you can send this question to all. This is a very good question. And it optimizes the transfer, because if you try to rebalance the data, it is better to rebalance in modular way rather than now moving the big file to somewhere else. Okay, because to divide something and distribute something equally, you will have to slice bigger pieces into smaller. Now it distributes the load to multiple machines. Why? Because if there is a movie PK which is quite popular and everybody wants to watch it, so first part of it would go into the data node 1, second goes to 2, third goes to somewhere else, and likewise out of 1 GB you will have 8 blocks available in the network, right? And when user want to watch it, so first user will be watching it on the first node. After 5-10 minutes, or maybe after say how many minutes, okay, so I'm just trying to do a computation. 180 minutes by 8 is how many? Okay. So after 25 minutes, it will be moving. The user who was watching the first 25 minutes will move to the second node and then move to the third node, because all the 8 blocks are distributed across the network. So that's how dividing the files into blocks made our other problem of availability clear. Now you may ask that we solved our distribution problem as well as availability problem in a single shot, but what about the backup? All right, now, okay, before I move to the backup, let me answer to Karthik. Karthik's question is it 128 MB or 64 MB by default? So earlier, few months back, or few you can say in the beginning of 2014, it was 64 MB the default value, but now everybody has adopted 128 MB, because those kind of disks are no longer available, where I mean below 2 GB hard disks are no longer anywhere available. Okay, so old disks generally keeps on getting eliminated. Why? Because the disk life is around 6 years. Okay, and disk anyway is a physical hardware where there is a movement involved, so there are high chances of failure, and that's why they keep on failing all the time. All right, so as of now, Mapr, Hortonworks, Cloudera, all three has 128 MB as the block size by default. Moreover, this block size is an interesting part. First, when you're trying to store file, you can also specify that, hey, this file need to be stored as 10 MB blocks or 20 MB blocks. Now, if you increase the modularity, if you have so many nodes in your network and you want to increase the modularity, you may want to break it down to smaller parts. All right, or you think that the kind of data we are dealing here, say you have 100 computers but your file is smaller, and you know that how to divide your data very well. Okay, or it is okay for you to divide the data in terms of fixed value. Then what you'll do is you'll decrease the size of block so that you have many pieces available across the network. All right. So this size of 128 MB is configurable while you try to write the data to the cluster. Okay, it's not something fixed. Also, in the all of this metadata is stored by admin node in the memory. All of this metadata is stored in the memory, while the the data node actually stores everything into the file system. So when you are constructing your infrastructure, when you are constructing your infrastructure, you might have to construct it such that the name node, the computer which is running the name node, is going to have the highest amount of RAM, while data node should have the higher disk space. All right, they should have a higher disk space. Also also, whether name node or data node, all of these things are processes. They are the Unix daemons or the services which keep on running. So these are the background processes which run and listen to a port. If you want to talk to data node, you will have to connect to a particular port in your computer. Just like any other services, if you are running a web server that runs on 80 port, and whenever you are saying http colon server and enter, so browser will try to connect to this server on a port called 80 port. All right, and all of this communication will be in the language called http or in the protocol called http. So in the similar fashion, the data node is also a process which is running on a particular port. Similarly, name node is also a process which is running on a particular port, and that also means that you can run admin node and data node on the same machine because they are running on generally different nodes. But it does not make any sense to run two data nodes on the same machine. All right. So that's how it is. Now next one is replications. So the point which we left out of our all problems is backup and failure, right? Now when we talk about, okay, on point number 2, smaller the block size, lesser unused space will be. Yes, you are right. But if you decrease the block size, what will happen is you will generate too much of metadata. You will have bigger index size on name node containing the information about which block is where. All right, because name node contains the information that this data node contains this block of this file, that data node contains this block of that file, and so on. So all of this information will keep on increasing the more number of pieces you have. Now now that means your RAM is going to get hit, and your name node will require a bigger RAM, and RAM is a precious resource. Also, your read speed will become slower because if you are reading the whole file in a single shot, it will have multiple hops if you decrease the block size. Therefore, it is just a coin toss that say, "Ki, let's have it 128 MB." Okay, there is no hard and fast rules for this. It's like saying while building a house, the bricks should be of this size or bigger size or smaller size. Okay, so it's just that so happens that everybody has chosen 128 MB because it's neither too small nor too big given current amount of hardwares we have. Does block size has impact on CPU usage? Yes, it would have, because if you decrease the block size, the number of hops your client is going to have is going to be very high, and therefore it is going to hurt your CPU as well. Great, great, wonderful questions. Keep on asking questions, and yeah. Now, we were talking about the failure and replication. Now, what will happen is, in case, now imagine this, you stored a file and your data node 1 went down. Your one piece is gone, which means the file is gone, because if one piece is gone, you cannot combine the rest of the two pieces to make it a complete file. So effectively, your whole data is lost, right? Therefore, it is Hadoop provides you a functionality by default that each block is going to have three copies, meaning three times of storage. Which say, so if you want to store one GB file, it is going to occupy 3 GB of space onto your cluster. Why? Because each of the block of this file is going to get replicated, and whenever something gets replicated in case of Hadoop, it's always replicated on other nodes. One copy of the block is going to be on the same rack as in having the same subnet, sorry, having in the same subnet, meaning the last digit of the IP address will change, while this next block, the third block, is going to be far away in the cluster. Why? Because because in case there is a fire in this data center, the other block, which is going to be in another data center, most likely if you have two data centers, your data is going to get saved. All right. And why do we have the first block on the same one? Because it is assumed, because the first block is on the same machine from which the client is connected. If you are running client from the machine 2, your file is actually lying on machine 2, and machine 2 is having data node 1. Now data node 1 is going to have your one copy of block. The next copies of the same block is going to be far away, sorry, is on going to be on the same subnet, on the same rack. The third copy is going to be in the another far away. If block size we decrease, then number of data node will increase. If block size no, not necessarily, Purushottam, not necessarily. If we decrease block size or increase block size, it is not going to impact our number of data nodes. Why? Because storage will remain same. All right. Now replication, in case of a replication, so each block is multiplied across the cluster. The moment any of this data node goes down, the moment any of the data node goes down, how does it know? Because name node keeps on pinging data node, as well as data node keeps on informing name node that, hey, I'm alive. The moment it forgets to inform name node assumes after some time that data node is down. And whatever was there on the data node on that machine, those blocks are again replicated, so that their replication factor of 3 is brought up to 3, because the moment a block is lost, the replication factor will be decreased by 1, right? Now there are only 2 copies left. To bring back the third copy, the data is copied again onto another node, and that is how the automatic backup and failure keeps on happening all the time. All the time that keeps on happening. Sounds good? Sounds good. All right. So this is how the replication works. Now the next one is the bottleneck. Somebody talked about, yes. What if name node fails? Good. We'll talk about this in a minute. All right. So what if, so the general assumption is this kind of a diagram. Whenever we have built our firewalls, whenever built proxies, this is the architecture we built always. Okay. So, okay. Uh, Let me just finish this. Right. So a typical server bottleneck is like this. So user always talks in to a server and server talks to the other ones. Now in this architecture, the biggest problem I foresee is for each reads, if I say to name node, ki, give me this file or give me that file. Now name node is going to become the bottleneck for everything. For everything, name node is going to become bottleneck. Name node has got a network card, and from that network card you have data nodes connected. Now same network card I got also connected to name node and said, hey, can you give me this file? Now all of this data which is coming from data node is going to get routed through the name node, and therefore name node is going to get hit really hard, right? Therefore, the architecture of name node is like this. Okay. So this is how this is how this is how it is avoided. So user, whenever you need a file, you will use a client. Client is a command line provided by Hadoop, and we'll show you a demo tomorrow on how to use it. So as a user, what you will do is you will talk to name node first and say, hey, do you know about this file? And name node will say, yeah, I know about this file. It has got these many blocks, and these blocks are available on these data nodes. The backup copy of these nodes is available on this data node. Why don't you go there and read your data? Right. Right. And that is how name node avoids itself to become the bottleneck. Similarly, when the data node is down, one data node is down and data needs to be replicated, blocks need to be copied. In those cases, it's not name node who is going to read the data from one and write to another data node and just to make the copy. No, it just instructs a particular node ki, hey, why don't you copy these blocks from that machine because one machine is down. So name node will just inform a data node to download copy or download the blocks from one machine to another, right? So that is how name node itself is clever enough to avoid the whole responsibility of reading writing data. But name node is also smart enough to own the responsibility of all of the metadata, so that if one user is writing the data, other user does not read it. How about, okay, yeah, another thing is, in case name node fails, there is always a backup name node or secondary name node, all right, which is like a hot backup. Not sorry, not hot backup. It's a cold backup. And there is any changes that happen to the metadata in the name node, those changes are propagated to the backup node also. All these data nodes, whatever they inform to the name node, they also inform to the backup name node. That is a past part of the HDFS design. So all of these data nodes are will inform the backup name node as much as they are informing to the name node, and therefore name node will remain as the main. Name node will have the backup copy or a mirror available in the network. The moment network goes down, network of name node goes down, or name node is corrupted, or something happens to name node, the backup copy which is prepared, which is just ready to take up, it takes the place of name node. All right, that is how it is done. Now how about synchronization between the nodes in case of replication? So Ramya, was I able to answer when I was talking about the data copy happens from node to node? Synchronization, yes. Okay, let me talk about a bit more about synchronization. Synchronization is the duty of the name node. Okay, so whenever you are writing the data or reading the data, you always inform name node before you do so. Okay, do we have service running on Hadoop client which takes care of this logic? Do we have service? Yes. So service running on Hadoop client. So whenever we say Hadoop client is not a service. Hadoop client is just a binary which does the division of data, and it has the logic of talking to name node. So Hadoop client is the one. Hadoop client is the not service. It's a binary. It's a logic. Is it? Am I connected? Hello. Hello. Huh. So yeah. All right. Only Purushottam and one more person got disconnected. Karthik got disconnected. Yeah. Very good question, Satyanaran. So his question is, do we have service running on Hadoop client which takes care of the logic of talking to name node and I mean, what was that? Call name node, store info. Yeah. So all of this logic is built into Hadoop client. Hadoop client is a binary, and Hadoop client is just like file system driver. Okay, it's a driver which basically through which a user is talking to the system. Okay, don't worry about this way that whenever you have to write a file you will have to go and look up name node and find all the information. No, you don't have to do that. Hadoop client does it for you. Hadoop client gives you the functionality of read write files straight away without having to bother about name node data nodes. All right, now so so okay, so all questions answered, I can move on. And synchronization is taken care by the name node itself. I'll show you this diagram. So this is another diagram representing the same thing. Name node is containing this metadata like this. It contains name of the file, folder location, number of replicas, and so on, and read write. So all of this is stored like that. All right, now we will go into the details more tomorrow. Okay, today what I want to tell you is that you can go to the admin console over here, or you can go to the hue. I'll show you the file system. Okay, so were you guys who is not able to log in into the our LMS? So first you log in into the LMS. Okay, so my courses, you will see the my courses. I'll go into the rest of the details tomorrow because today it's already 5 o'clock. All right. So which one is yours? I'm sorry, I have too many courses in place. Yeah, we'll go into the more details about the client. Okay. Now, to be a little hands-on, you can actually, first go through here. The new today's session will be available along with the old one. All right. Now, installation instructions you should go through, as well as you should take the quiz. All right, should take the quiz. Some of the questions you may not be able to answer. Do not worry, skip those questions and attend those questions again. All right, now Hadoop installation, you go into the details. The password, login, everything will be available inside the Hadoop installation. Once you have done that, you can actually go into you will know the password of these things, and you can go to hue is a beautiful UI interface from which you can access the file system. So this is how the file system would look to you, just like your Windows folder. This is HDFS. Some, it has got data nodes, it has got those name nodes and whatnot. All right. And similarly, whenever you are managing a cluster, you will be interacting with 8080. This is 8000. This is 8080. Okay. Now, in this one, you will see that there is something called name node and there's something called data nodes. All right. So you see that here it's giving me a warning saying secondary name node is stopped. Okay. That's the backup name node I was talking about. It's similar to backup name node. Now I have got here in HDFS, it shows that name node is running and there are 4 data nodes and all 4 of them are alive. All right. It shows you those details. And also when you go to the dashboard, the student account has the access to this. Student account can not change any of the services. Okay. And when you are dealing with this file browser, create your own folder name and put your files in that. All right. So we'll see you tomorrow, and yeah, we'll go into more details tomorrow. All right. All right. So yeah. So today's 15 minutes are lost, and that's what has been left. So we'll continue from where we have left. We'll continue from here tomorrow, and see you tomorrow. All right. Bye bye. Great. I hope you like it. You will get a questionnaire asking the feedback. Please respond to that questionnaire. All right. Bye bye. Have a good day.